So yeah, we've seen before, so just a short motivation. Well, we've seen before a lot of methods for basically access parallel clusters, but there may be more than simple feature relevancy, independent relevancy, because I mean access parallel subspaces of course have the assumption that the features are not correlated. Yeah, so they are not dependent, so they are independent. So this is an independent feature independence assumption if we focus on access parallel subspaces. And obviously, and we have seen some examples before, this is not the case in general. And in practice, very often features are correlated. So the subspaces or the clusters do not live in or exist in access parallel subspaces, but also in arbitrary oriented subspaces. And here's the example of this metabolic disease data set where, okay, cluster 3 is actually an access parallel subspace cluster. So here is the subspace where cluster 3 or the points of cluster 3 are dense or very similar to each other. And this is actually access parallel. But cluster 2 and cluster 1 are obviously subspace clusters in subspaces that are arbitrary oriented. So this red one here is the subspace where those points of cluster 1 are very similar to each other. So this is obviously an arbitrary oriented projection or subspace. And the same holds true for the subspace of the relevant subspace of cluster 2. Yeah? I'm sorry. So the question is, can the methods introduced so far capture those patterns? Well, I already told you that there is some kind of no. The answer is no, but to some extent they can capture that. So we will have a look at that. Well, subspace and projected clustering methods obviously are only restricted only to access parallel subspace clusters. So they assume feature independence. They could potentially detect cluster 3, but they have no chance to detect cluster 1 and cluster 2 because they are not in access parallel subspaces, obviously. Yeah. So those methods will not do the job here, or at least the general job. What about pattern-based methods? Well, they can actually find simple pairwise positive correlations if we take the variant with the coherent evolution patterns. However, negative correlations have no additive pattern. Yeah, so coherent evolutions, they need to they will find additive patterns. But if we have a negative correlation here, so you see those points here, if you want to cluster them, if you want to, the perpendicular subspace here, perpendicular to this line here, will be a subspace where those points cluster very, very well because they are more or less the same. So they are very, very similar to each other if you project them on this subspace here, which means that those points here have a negative correlation. Yeah? And if you have a look at the parallel coordinate visualization here, then you see that this pattern here cannot be found by coherent evolution patterns. Yeah? So this is not a coherent evolution pattern. So the pattern-based methods, especially those that look for coherent evolutions, they are able to find pairwise positive correlations, but only those. Yeah, and there are much more correlations that may happen. There may be pairwise negative correlations like this one here, and in addition, there may be even much more complex relationships between more than two features. So pairwise positive correlations means we have a positive correlation between two features. But if we have, I don't know, hundreds of features, there may be much more complex relationships between several features, and they are completely out of scope of those pattern-based approaches. So here is an example. The data set here has a very complex correlation among three attributes in that case. Yeah, so you can think of those are only the relevant attributes here, and the correlation is a1 minus 2 times a2 plus a3 is equals to 0. Yeah, so there is obviously a correlation going on between, and very complex linear correlation going on between three attributes, between these three features. Well, if you have a look into the feature space, those 3 points here depicted here in the data matrix, they are all located on a common hyperplane. Yeah, in that case, in a 3-dimensional feature space. So we have the 3 features, A1, A2, and A3, and those points that have a complex linear correlation, they are on a specific hyperplane, on a common hyperplane. Yeah, but again, the parallel coordinates look completely weird, so the pattern-based approaches cannot find any pattern here, even the coherent evolution patterns. Yeah? So we can summarize that we have well, pairwise positive correlations. So positive correlations between 2 features can be detected by coherent evolution pattern-based approaches, but pairwise negative and more complex relationships where several features are involved cannot be detected by those pattern-based approaches. So well, we need some more sophisticated approaches, and those are the so-called correlation clustering approaches. Once again, a warning. So in the community correlation, in the research community, correlation clustering is used ambiguously, because some use it as we use it here in the lecture, where we want to find clusters in arbitrary-oriented subspaces. But correlation clustering sometimes also is a synonym, or is a special thing in spectral clustering. Yeah, so don't be or don't get confused about that. And we will use correlation clustering only or solely for the methods that search for arbitrary-oriented subspace clusters, because they are somehow obviously have a common correlation amongst a subset of the features. Yeah, that's why we call it correlation clustering. So how can we do that? But what is the general idea for the correlation clustering? Well, to find clusters in subspaces of correlated attributes, meaning in arbitrary-oriented subspaces, a more general approach is necessary. Okay, we talked about that. And yes, as I said before, the difference. And the basic assumption is that any cluster is located in an arbitrary-oriented affine subspace S plus A of the d-dimensional space. Yeah, so that is A here, so that the subspace, the subspace needs not to be through the origin. Yeah, and S is actually the subspace here. S defines this hyperplane here, this subspace. Yeah, and if we project all the points onto this subspace here, then the points are more or less dense or extremely similar or whatever. So fulfill a specific cluster criterion. Yeah. So that is the basic assumption of correlation clustering, that we have a cluster, and if we project the cluster on the right arbitrary-oriented subspace, which is this S here, then those points fulfill or meet a given cluster criterion. For example, are dense or are very similar to each other or whatever, are compactly packed or whatever. Yeah? So that's the idea.